Okay, so let me give you the problem setting first. All right, so we are looking at the functional brain network, okay? In particular, we try to study the brain networks of people who have this Alzheimer, did he say there? Alzheimer disease, yeah, Alzheimer disease. All right, so you can already see from the image that there is some difference between the normal image and Alzheimer disease. So we are trying to develop a method to actually differentiate them. All right, so we actually use this as a brain networks, and we hope by an earlier detection, we can actually give a series of diagnoses and also treatment for this neurodegenerative disease. Okay? All right, so the first question is, why do we want to model this as a dynamic network? Okay, so let's see how static brain networks construction is done. We have some MRI image, and then we actually get blood oxygen level dependent signals. And then we somehow compute it into correlation matrix. And then with some threshold, we build these functional brain networks that tells you how one part of the brain reacts with the other part of the brain. Okay? All right. So you see in this process, we actually compress the information with time information, compressed into a static correlation matrix, and then subsequently a static functional brain network. That is why we lost some information on the time dimension. All right. So we think that we hypothesize that with the better modeling of all these dynamic images, we should be able to capture the signal more precisely. Okay, so instead of having the signal processed together into one correlation matrix, now in the evolving functional brain network, okay, we actually separate the signal, the both signal into different segments. And for each segment, we actually generate a correlation matrix, okay? That is called a snapshot of the correlation matrix. And then from each correlation matrix, we then build a functional brain network. So instead of having just one static brain network, now we have a series of functional brain network, and that is called evolving brain network. Okay, so we assume that brain activities is constantly changing over time, and our model is expected to capture such changes and accurately express the brain information. All right, so this is the setting. I hope it's clear. Okay, so with this setting, we actually use graph kernel to compute this. Graph kernel actually computes the similarity between two graphs, and the dimensions that we can compare similarities includes topological measures, then other things like, of course, you can also carry on deep learning, and then usually for graph kernel method, we measure the similarity of the structures. So this is powerful generalization ability on high-dimensional complex problem, because instead of having the high-dimensional expression for each node, now we actually express their similarities, which it is expected to have a lower dimension, right? And we actually focus more on the topology of brain networks, and this is also more adaptive to various data sets without much need to tune parameters. All right. So, for example, for the graph kernel of this tool, with each with the P in the center, the P is node 1, P considered as one particular region in the brain network, okay, we can compute which are the Q equals to 1 degree neighbors, and which are the 2 degree neighbors. So you will see that from the left graph have 2 degree 1 neighbors, 2 degree 2 neighbors, but in the right graph, we actually have 3 degree 1s and 1 degree 2. Okay, that is why there is some difference in the structure of these two, right? And that we call as a graph kernel. All right. So just now it was graph kernel for two static graph. Okay. Now we have to come to this graph kernel of involving brain networks. So instead of comparing two, 1 to 1, okay, now we are comparing a set of 4 snapshots to another set of 4 snapshots, okay? So, and sometimes the length may not be the same, okay? So 1-to-1 matching is infeasible in this setting. So we are considering whether there is another way to actually match the graphs, so to achieve optimal matching, right? Okay. So the first method we propose is called GMGK, Global Matching-Based Graph Kernel, all right? So we actually have the sub-network kernels. The A is an adjacency matrix. AX means we actually flip the adjacency matrix into the order of X to compute what are the neighbors with respect to each individual, all right? E is a vector of all ones. So when we have AX power E, that is actually computing the X order of each neighbor, all right? So then we can compare these 2 degrees together. And then we come to this functional similarity between chi and xi, right? The chi is actually the first subject, xi is the second subject. And the subscript P here, it is actually with respect to one particular region, okay? We call that region as node P. And it is an average of the exponential of the Q from 1 to H. Think about Q is 1 as 1 degree neighbors, Q is 2 degree neighbors. So we are actually measuring the difference between the similarity between each set of neighbors, okay? 1 degree neighbors compare with another 1 degree neighbors on the other side, 2 degree neighbors we compare with another 2 degree on another side, okay? So this is to compare the similarity between 2 corresponding regions. And then we average all the regions together, becomes the kernel between chi and xi, right? So that is equation 3. Okay, so this is the first measure. So you can see that we can capture the dynamic change from one snapshot to the other, okay? Basically for each timestamp of the first subject, which is the 1 row above. And let me see whether there's a laser here. Each snapshot of the first subject and each snapshot of the second subject, we compute their similarity, and that becomes a bipartite between the first subject and second subject. All right. So for bipartite matching, all right, we have the standard Hungarian algorithms to compute what is the best matching under this setting. All right. So that is the first GMGK method. Okay. So similarly, we actually compute the, you see the weight of each H is the kernel between xi and between chi and xi. Okay, so GMGK will compute the optimal matching for this bipartite graph. The second question, we actually want to somehow put some constraint to say that when you have the first matching, when you have the matching should somehow preserve the ordering as much as possible. Okay, we don't require the ordering to be exactly the same because for two subjects, their sequence of brain activities may not totally the same. Okay, so it could be that, you know, the first person think about seeing 1, 2, 3, then 4, 5, 6. But the other one could think in the order of 2, 1, 3, then 6, 4, 5. So it could be, okay? But roughly speaking, the order should be somehow preserved with some local arrangements, okay? So that is why we considered the second method, which is local matching-based graph kernel, all right? So one way of doing this, it is actually using dynamic programming. But if we use dynamic programming, the number of states that we store will be too many. Because remember, this is an approximate matching. This is not the exact problem. So for approximation problems, we actually have a lot more states than the exact problem. Okay, so we actually proposed a constraint that we limit the number of snapshot position changes, which means in the bipartite graph, we would like to minimize the number of intersections of the edges. Okay, so for example, if we have this matching, we have 4 pairs, right? But we have 3 intersections. So when we have 3 intersections here, means that the order is not pretty much preserved. Okay, so that becomes our second objective. We want to minimize the number of intersections as much as possible, provided they actually achieve the same GMGK in the first step, okay? So in the first step, they achieve GMGK as large as possible. You maximize the similarity. In the second step, you know, we want to minimize the local match-based graph kernel, which is to minimize the number of intersections, okay? So we combine these two together to ensure that the difference between location index is no more than this D, and this D becomes one of the parameters in our model, and we limit the number of H crossings at most C crossings. So this becomes a constraint. Okay, so LMGK, although there are some H intersections, but largely speaking, it can retain natural changes property of the dynamic brain network, okay, with some local arrangements. Okay. All right. How come it's not working? Okay. So when the number of H crossing is greater than the threshold C, we actually just skip this matching. All right. When the number of H crossings is less than C, we calculate the weight W. So then after that, we select the W, which is the best so far, that is greater than the current matching. Otherwise, we save the last matching. All right. So quickly, I will go through the experiment sets. Do I still have time? 30 seconds. Okay. So we have these two sets of MRI data. Okay, one is ADNI, the other is OSIS. So roughly speaking, you can see the data is quite balanced. All right. So we actually use accuracy as the measure rather than using precision or recall. All right, so first graph, we actually compare the different kernels. We compare our methods together with SGK. SGK is a static graphic kernel. So we see that for both GMGK and LMGK, there is a significant improve from SGK. And then we also test our parameter of the model. For example, we can tune the threshold of the brain network. Okay, we can also tune the number of snapshots. And after that, we also tune the scale of subnetwork H. Remember, our Q takes from 1 to H, right? All right, so the optimal value is at where H equals to 2. We also have this power iteration D. That means how many times that you flip the adjacency matrix. So D is 4. Okay, and we also limit the number of H crossing C. And then the optimal value seen here is actually at 3, which is not very large. Right? So with our method, then we pair with the machine learning classifier. One is logistic regression and the other is SVM. So we see that because SVM is more complicated than LR, so it is expected that the SVM actually give a better accuracy. And we can also compare with different methods for comparison. We compare TME, topological measure extraction. We also compare dynamic feature extraction. So you see for these two, our method actually has a significant increase. So you can refer to the paper for more detailed analysis. All right, so I don't have more time, okay? I would like to conclude that this is an effective method to find the optimal matching, all right? So in order to preserve the natural characteristics, we use LMGK on top of GMGK. Yeah, okay, so that's all for my talk.